So we're going to be talking about MPI optimization techniques. Some might even say this is more of a fairly low-level MPI, getting into some of the MPI internals things. We were just discussing it's difficult to know what's the right level of MPI. This is not an intro to MPI talk. This is kind of like what's going on underneath the covers a little bit. Maybe you'll think about it in the future, or maybe you won't, or maybe you'll just have it in the back of your mind. I found it useful to have it back in the back of my mind sometimes. Oops. So right now we're going to talk about how MPI works. We're going to give a few hints about performance then. First thing is that everyone should realize and know, and we must confess that the Cray MPI uses the MPICH2 distribution from Argonne. So whatever they are providing, we're picking up and then modifying and tweaking a little bit. But many of their algorithms in terms of implementing the MPIQs and progress engines and whatever are theirs. It does provide a good, robust feature set. We don't have to go and reinvent all of that stuff ourselves. We then provide the low-level communication binaries that MPI feeds to that. Collective tuning was what we do. And then also for the shared memory device, if your two endpoints, the source and destination, are both on the same node, that is intercepted, and it actually turns into a memory copy using XPmem. I think XPmem is just a Linux thing. It's intercepted and just as a shared memory copy. That is much faster. It doesn't have to be bounced off the Aries at all. It's got lower latency. So that's a nice way to do that. Many layers are straight from MPICH2. Error messages can be from MPICH2. Not all error messages are from MPICH2. Obviously, if you see something about Aries counter coming out or DMAP coming out, that's our own special thing. This is the same slide I had before. It's basically reiterating that they behave essentially the same on the XC and on the XE. We have this thing called the UGENI interfaces, the same. UGENI used to stand for User Gemini Network Interface. Is that what it says? UGENI interface. But and then they said, well, we'll just keep it and change the G from Gemini to generic. So they kept it around. MPICH2 goes essentially the same. And then there's different message paths, and we're going to go over these paths in just a second. Short, eager, and rendezvous, that's all identical. And the enhanced features I talked about this morning with the asynchronous progress engine and the collectives. So the basics, we're going to go over the day in the life of the MPI message. And some of these things say Gemini, but this part is all identical between Gemini and Aries. So there are four main pathways through the MPICH when a message is actually sent from one rank to another. And those messages are two eager paths named E0 and E1, and two rendezvous paths known as R0 and R1. And which one you take is based on message size. So if I'm reading this right, okay, the top bar here is the message size in bytes, and then kbytes and megabytes. And the eager 0 is less than 1 kbyte is how I read that. E1 is 1 kbyte to 8 kbytes. R0 is from that size up to 4 megabytes. And when you do a message size that's larger than 4 megabytes, it's actually R1. There's different environment variables, and we'll list these environment variables again later, about when these different, not barriers, crossovers happen. And you can change this a little bit. Some people, you know, if they're, for example, if you're right on the edge and just at the, just above 8K, your message sizes, you know, are just above 8K, but you have reason to believe it will be better to do with an eager message instead of a rendezvous message. You can change this to be 16K, and then it would capture that. But you don't necessarily, you know, these things represent mailboxes and stuff like that. So it's not that you can actually do a eager message that's, say, 1 megabyte. You would blow the memory on your nodes. So the eager protocol is that data is transferred when the MPI send or variant of send, I send, you know, and then I think the send receive and S send, all those guys, you know. It's transferred when the send is encountered. This implies the data will be buffer on the receiver's node. So when the sender hits the send, it says, no matter what, I'm going to send it, right? It doesn't matter if the receive has already been posted or if it hasn't been posted or if there's an I receive or not. It's just there, I'm firing it over. Well, in order to send it over to someplace, that implies that there's a place over there waiting for it to be received. And that's why there's a buffer over there. 2 eager pathways is E0. These are small messages that fit in what's called a SMSG mailbox. I just call it mailbox. And then this default mailbox size varies with the number of ranks in the job. It sort of makes sense that, you know, as you get up to larger and larger number of ranks, if you have a fixed mailbox size that might have made sense when you were talking about 1,000 ranks, no longer makes sense when you're talking about 100,000 ranks. And, you know, literally where our MPI library is spanning from, you know, a few tens of ranks to, it's been tested up to 700,000 now. So it goes pretty high. So this is the environment variable that you can use to adjust that size. So the E1 then is too big for the mailbox, but small enough to still go eager, and you can adjust it with this size. And the thing is that there are extra copies that are required for this one. And I think we're going to go over, actually travel that in a bit. So as I said, okay, so the mailbox size varies with the number of ranks. So the protocol message can fit in the mailbox. So on the left-hand side is an example of the number of ranks in the job. This is an older one. This is a newer one. They're probably well beyond 5.5 now, right? Isn't it 5.5 is the mailbox? So I think we'll use this one. So when your ranks are 500 and when you're using 512 or less ranks, it can go up to 8K bytes, but you can see as you grow it, it's going to go down to 2K bytes, 472 bytes, and 216 bytes. And this is to just limit the total amount of memory that where the MPI is actually consuming as you scale up. There's other presentations where, you know, we've been told and others have collected data that, you know, a generic white box MPI, they don't do these kind of adjustments, or they have other issues. And as you use more and more ranks, actually more and more memory of your node is consumed by the MPI library itself. So day in the life of a type E0 message. We have a sender on the left-hand side, a receiver on the right-hand side, and then we have the mailboxes, which are these little memory locations that are set aside on the receiver side. The sender, just as soon as it hits the send, sends the data. It also sends the header, and the user data, sends the header along with the user data. So, and then if the user data is 16 bytes or less, it is actually copied into the header itself. And the header is, I don't know how big it is, but we're not talking just a few bits. There's several bytes of information, and maybe even several words worth of information in the MPI header. So when you get small messages, latency and various rates matter more, but you're still transferring around quite a bit of data. So the data gets put in there, and then I think the CQ, I don't know what the CQ actually stands for, but you know, the information is put into a little queue that says, hey, a message has arrived. And when this guy actually hits a receive, or the progress engine recognizes that a receive has come in, then it's going to have to look into the CQ event and decide, oh, you know, something is actually there, something valuable is there, I have to process it. But you can see direct, immediate. If you're trying to overlap communication and computation and you have a short message, this is basically happening immediately, and it will return. I don't know if it quite returns before it arrives over here, but you can think of it, you know, you can think of it either as getting the asynchronous automatically, or more importantly, though, it doesn't have to wait for the receive to be posted. Now here's a type of E1 message. So instead, what happens is this is just the MPI header is sent over to the mailbox, not the user data. The MPI header is sent over to the mailbox. Something is put into the CQ event, and then when the receiver actually issues a receive, or the progress engine recognizes that a header is over here, it now knows where to process it. The sender, before it sent the header, did a memory copy from its user space into a buffer space that's right here. You don't need as many buffers in as MPI ranks here. You just need as many buffers as you want to have eager messages in flight per rank, which is a much smaller number. And here it says down in the corner, the number of buffs default is 64 buffers, each with each up to 32K in size. So 64 buffers is a lot smaller than the number of PEs for the majority of size. So that's why we can use this one. So again, copies it into this buffer, sends the header. The receiver recognizes that the event has arrived, and then it does what it's called an RDMA get, which basically, in terms of what's happening in the hardware, is that the hardware, the receiver initiates a request to go get the data, and then the data is moved back this way. It's copied into an internal buffer and then copied finally into its final memory. So we have buffers on both the send and the receive side. Again, so think about this for a minute in terms of asynchronous communication, overlapping communication and computation. The receiver is the one doing the data movement. So in that regard, it's not quite asynchronous. But in terms of the viewpoint of the sender, well, the sender basically is done, from its perspective, the send is complete as soon as it's copied the memory into this buffer and sent the header. That's true more or less. There's a little bit of bookkeeping that comes along here, but I think in terms of forward progress, it can return from the send and continue on with computation. So you can see where this system allows the data to, the sender doesn't block waiting for the receiver. The receiver can process this whenever. If he's late, he can go ahead and process it later. If he is early, then you either need a progress engine to recognize this, or it will happen at the wait all that will process. Now these messages are not very large, so you're probably not trying to overlap a lot of bandwidth with communication, but it's nice that there's this flexibility in there to allow the sender and receiver to kind of get out of order a little bit, or out of sync, I should say, with each other. I'm not sure. Yeah, I mean, yeah, I'm not sure what it does. I mean, these, yeah, I really don't know the answer to that. My guess is that if you do an MPI put, then it would do an RDMA put. But I'm not 100% sure on that one. So this is, the one thing to note here is if your message, does it say this on the next? Okay, so now is as good a time as any. If you refer back to the async progress engine slides, okay, we said that only applies to the rendezvous protocol. Okay, it doesn't apply to the eager protocol. So that's one reason why that async might not apply to everyone, is that some people have message sizes that, the important ones at least, are less than 8 kbytes, and they're just fine and dandy with the eager message. Turning on async is not going to help them at all. But if your message size is larger than the default, by default, if it's larger than 8K and less than 4 meg, then it uses the rendezvous method known as R0. You can use these environment variables to adjust the starting and end point. And you can, this is where we think of the best opportunity to overlap communication and computation. Like it says, it helps to send, well, this says it helps to issue I send prior to I receive. And honestly, over the years, I've seen this flip-flop. 6 years ago, we said to do I receive before I send. But apparently with this software package now, and I do believe ever since Gemini, they've been saying I send is issue I send prior to I receive, if possible. Now, I will tell you, I've seen parallel programs, watch them happen. The idea that there's really, because I moved I send before I received in the program, that the I send is going to happen before I receive. Things are going out of sync really in the actual computer, so it's a little more fuzzy than that. If it's larger than 4 megabytes, then we do an R1 pipelined put. And then, this is message, doesn't this conflict, these two data points? This says it's used for messages larger than 512K, and this one says it's up to 4 meg. So I have to double check on that one. I'm almost certain it's 4 meg. The thing here is, well, okay, let's go on and actually go see what this is the R0 method. So this time, we don't copy, the sender does not copy the data into a send buffer. The assumption here is that the amount of data that you're sending is now too large for those 64 buffers in general. And so it's stuck in, it's left in your user memory. It does send a message with the MPI header to the mailbox, and that in turn puts something in the CQ queue, and the receiver, once it's issued the receive, I think this is why it's better to pre-post the sends. You want the receiver to recognize that something is in the CQ event as soon as it does the receive. If this event gets here before the receiver looks, then you have to rely on the receiver looking again somehow through progress engine or whatnot. So once the receiver recognizes that there's something in the CQ event, it evaluates the header, and then it can initiate an RDMA get. And again, it doesn't move it between buffers. It does it directly between this sender's memory and the receiver's memory. Once that's complete, then it can issue a done statement. Then the sender knows that the memory has been cleaned. So there's no extra data copies, and that's a little bit nice. You don't want to be sending over too much data, but you're relying on the sender initiating this. If the sender can initiate the RDMA get, the hardware is actually able to process the RDMA get while the sender moves on, or the receiver moves on. So that is what gives us our chance at overlapping communication and computation. But the key again is that the receiver has to recognize that there's an event, and it has to initiate the get. It doesn't have to move the data, but has to initiate it. The R1 type, on the other hand, is a little bit more complicated than that even. So let's see I get this right. So the sender sends the MPI header to the receiver, puts it in a CQ event. The receiver, the receiver recognizes something, sends a CTS message back to the sender when it's received, and it's posted it's received. Then it says, okay, the sender chops this up into a bunch of chunks and starts issuing a series of puts over into the receiver's memory. And then it says repeat. That's why it repeats 2 to 6 until all the sender traffic is transferred. So if this is, I'm going to pick a number. I don't exactly know, but let's say you're sending 20 megabytes of data. It might actually have to process that 2 megabytes at a time, and it's going to send a chunk, send a chunk, send a chunk, is how it has to do it. I'm not exactly too sure exactly when it's sending those chunks how much back and forth communication there are, but I do know this is another example of where you need that async progress engine in order to do overlapping of communication and computation. If you don't have the asynchronous progress engine, even if all the stars align and it starts up one chunk, it'll start up one chunk, and then if it goes off and does computation, it won't start the next chunk until it gets to the next MPI call, for example. So you could do an MPI ISend. It actually starts up a chunk. It goes off and does a computation. In our little example where we moved 20 megabytes of data, it would when it comes back to the wait all, what has actually happened is that 2 megabytes of the 20 megabytes has moved, and now the other 18 megabytes has to be moved during the wait all. And so you can actually see this on Gemini with some tests. The classic example to test overlapping communication computation is to literally, set up a 100 megabyte buffer that you want to send, issue MPI ISend and IReceive, then have everyone go off and do a big matrix multiply, and then return and sit on a wait all. And what you actually find is that if you time the wait all, there's just a whole bunch of time in the wait all, spent in the wait all. And that's because the message size was so large, almost nothing happened in terms of overlap, and then all of the transfers happened in the wait all. The async progress engine is what really helps that, because it's the one that keeps on checking, can I initiate another chunk? Can I initiate another chunk? So the environment variables affecting the pathway, this was scattered over the thing, over the presentation already. we have a short message, eager message limit, ND reg max size. I'm not too sure why they chose that name, but this is the name that controls when you switch from R0, maximum message size for R0, and then you can actually disable the entire rendezvous path, and I think this is disable the R1 path if you really wanted to. So you can see, I think one of the things that's good to keep in mind is that, all I have to do is issue an I send and an I receive, and it's done, right? And there's actually a lot of mechanisms that are going on underneath, and as your message size transitions from one to the other, you can actually get quite a bit different performance behavior. So if you're ever in a situation like that, as you're scaling up your job and your message sizes are shrinking, remember that these things could be changing underneath you. And again, I've had this earlier in the morning. I've been referring to it constantly. You know, I think this is really an interesting thing. We've only really begun to dabble with it in terms of this new hyper-threading thing. But this async thing is what is going to be the thing that checks to see if there's a message in the queue, checks to see if there's a chunk to be processed. And if that's checking in the background, it will be able to initiate the communication and start the transfers while the main core is doing the computation. And it says here, relies on BTE for data motion. I didn't really go into what a BTE is, but it's a block transfer engine that's built into the Aries. So even if it's transferring 2 megabytes, the Aries is capable of transferring 2 megabytes all by itself. It doesn't need the processor at all. All we need the async engine to do is actually initiate the transfer. So the async engine, I think, is doing relatively little work. So, you know, environment variables, I'm going to run through the following slides quickly, check for MPI, man MPI. I've even cut this down compared to some of the other presentations that I've seen. So I only have 4 slides. I think there's an enormous number of MPI environment variables that you can read about and play with and ask questions about. Most people don't play with very many of them, if any of them, but at least you know that some of them are out there and exist. Yeah. So short messages versus long messages, what's the recommendation is the question. You know, I think that the standard MPI optimization is to pack and send. And I think that's probably a good idea to a degree. I don't think, you know, if your messages are 10 words or something like that, that overhead is really going to start to eat up stuff. So packing those kind of messages up is going to be a good idea. I don't know exactly what the curve looks like, but you know, to me, do you require 1 megabyte messages? It was probably it was a pretty good idea on C Star, but I don't think it's required on Gemini. So so I think that E1 works pretty well, but if you overwhelm it with too many messages, then just fewer MPI calls is probably better than, you know, 10x the number of MPI calls. So I think it's a good idea to pack. I just don't know exactly when is the diminishing return, I guess, is a good summary without answering your question. So I think somewhere I might even I have to look at maybe if I have any kind of curve that shows performance versus versus message size if there's a plateau. I'll try and look at that later. So these are environment variables. I think we already talked about these, the V-short, eager, RDMA threshold. We didn't talk about RDMA threshold. This is the threshold that actually kicks in and uses the block transfer engine. I believe it's basically set currently to the same as the max eager size. And we've tried to, some of us try and play around with this a little bit, but the defaults are pretty good. And sometimes the defaults change with PE count. But at least you know they're there, and if you're trying to play around with asynchronous, maybe you just want to play with these and see if you kind of fall into a local minima. Here's another one that's a bit out there, but in case anyone tries this, they know it. This one is only relevant if you mix MPI and SHMEM or UPC or co-array Fortran. And basically, that's common if anyone tries SHMEM, UPC, or co-array Fortran, because the number of applications that are pure SHMEM, pure UPC, or pure co-array are really small. Most of the time, what we're doing is we're taking an MPI application and adding these guys. So if you find yourself into that situation, you may need this environment variable. And so basically, this is enabling MPICH and DMAP to share the same memory registration cache. These are low-level things. They have to register the memory. Conversely, you might have to disable it for SHMEM codes that call SHMEM init after MPI init. I think the next slide, we have the actual error message. But this is what you do. You set it to export it and set it equal to disable. Basically, if you're mixing these things and you get an error that looks something like this, all right, and this is, don't try and memorize that page. But if you're trying to mix it and you get an error, ring a bell, go back into some documentation or ask someone, hey, I think I got this error and I think there's an environment variable that I need to set, and then the error will hopefully go away. Another one that's may be important or you may not care about it, but it's good to know, is this dynamic connection thing. So, so normally we want to leave it enabled. This is enabled at default so that mailboxes, resources, NIC resources are allocated only when the application needs them. So this basically says that when two ranks need to communicate, the first time they communicate, they need to set up a certain amount of resources, be it in the NIC or a mailbox or some kind of registration or some kind of handshake. The first time that happens, the resource needs to be set up if you have dynamic connections, right? Now, if your application is an application that does something like nearest neighbor or relatively point-to-point communication, even if you're an AMR or unstructured grid code and you have 20 connections, well, 20 connections is a lot fewer than 2,000. And so it's probably a good idea to leave the dynamic connections on. However, if your application does all-to-all, and it really, if you think of one-dimensional all-to-all, where every rank has to communicate with every other rank, this will result in a significant amount of connections being created and may actually take a measurable amount of time. This is important, I would say, mostly for the use of benchmarking, because if you're running a relatively short benchmark to test MPI, and you run this thing, you run it with dynamic connections, depending on that communication pattern, you can actually be timing those dynamic connections. And I don't know, there's no one thing that says, well, you have to run this long before you don't have to worry about it, because it all depends on your traffic pattern and the number of nodes. For example, on Blue Waters, if you tried to do this across 300,000 300,000 or 700,000. I can't remember which one's a really bad one. But it would literally take 30 to 40 minutes to do all of these connections. And if you wanted to time an all-to-all, you would actually, to reduce this noise, to say, do the connections before you even hit main, then you can disable this, and it will do all the connections before it hits main. Now, it may take a half an hour to reach main if you're running on Blue Waters. Not on Daint, probably, but if it can take a little bit longer to hit main, but hopefully your data is less noisy after that. So it's probably mostly for benchmarkers. If you're running a real science app that runs for an hour and uses a few thousand ranks, you're not going to notice or care very much one way or another. The connections are going to happen either way. You only care about the time to, when your prompt returns or when your job finishes, and it's going to be relatively even. One way or the other is going to be relatively the same thing. It's really if you've shortened your job and you're trying to communicate, trying to understand communication, and if you're getting puzzled, you might just know that there's this thing out there, and if you disable it, there's a chance it will reduce this noise. So. Those are my MPI environment variables. Now I'm going to talk about rank orders. And one thing, this was really important on C star. People had, it was probably a little bit less important, but some people, it was still important for some people on Gemini. And we've been talking about it long enough, and it's probably still relevant on Cascade, but we have we're less sure exactly where it will fall on Cascade in general. But basically the thing is your nearest neighbor really your nearest neighbor? And do you want them to be your nearest neighbor? Who are your neighbors? So you have this idea in MPI logical space that I'm communicating with PE +1 and -1, and maybe PE plus n and minus n. Well, +1 and -1 are probably on the same node as me, but plus n and minus n, I don't know where they're at. They could be some distance away. So what can we do to affect this? Well, we have this environment variable called rank reorder method, and there's really 4 different settings. There is 0, which is round robin, and that puts a rank on every node on the list until it gets to the end of the number of nodes, and then it wraps around. All right. I remember the Intel people a couple days ago. They talked about a placement called scatter. This is like that. You scatter across the whole machine, then you wrap around. It's a interesting one to have, and if you have really kind of load imbalance, but you don't have any kind of nearest neighbor +1, -1 communication, maybe this kind of rejiggles how your job got set down on the machine, and therefore could come up with a different performance profile, and hopefully different might mean better sometimes. So it would be something to try. I think that I would most likely try it if I really had different degrees of computation in different PEs. The default is the SMP style placement. That's fill up a node and then move on to the next node. And the way we fill Rosa is fill up a node and then move one step in the grid and fill up a node, and move one step in the grid and move fill up a node. Now, we don't always move a step in the same direction. We kind of snake through the system. But so those are also close. Currently, the policy on Daint is fill up a node and then fill up another node in the same group, fill up another node in the same group. And I believe it's, more or less fill up the group and then move on to the next group. So that's the SMP style. That's the default. That's probably the easiest one to think about. The folded rank placement, similar to round robin, except for instead of going all the way across and going back to the beginning, it goes all the way across and then folds back on itself and goes backwards through the list of nodes, and folds back and forward to the nodes. And then the one that's used probably the second most often after the default is the rank order one, where you actually give it a file to tell you, I want to do my own ordering. And so when is this useful? Point-to-point communication consumes a significant fraction of the program time, and load imbalance is detected. You might play around with those things. Shown to help for collectives all-to-all on subcommunicators. We'll revisit this, I think, as we get more experience on the cascade systems. So from the rank page, man page, basically what I'll read out of this is there's this rank reorder method 3, and there's this grid_order utility that allows you to say, oh, well, my job is a 3D decomposition with the following dimensions. You read the man page, you look at how you use grid order, and grid order will rearrange it in such a way that you can turn something that's logically your neighbor in Cartesian space into something that's physically your neighbor on the same node. And I'll have CrayPack can also make suggestions as well. So a case study might be something that helps you understand what we talk about. I'm not going to go into super deep depth here. And yes, this was on Gemini, so we're going to revisit this as we move to Cascade. But it's earthquake code, XYZ structured grid, uses 2 communicators, shared memory on node is fast. Well, Eugenie, between nodes, it's not as fast, right? We think it's faster than Rosa. It's pretty fast, but it's not as fast as shared memory copies. So we have a 3D grid of blocks, and we want to, each block is mapped to a processor, and we want to minimize the amount of communication that goes off node. And we're going to do that. Instead of doing linear, we're going to do some kind of block ordering. So in order to generate this file, we load the perf tools, and we read the man page, and we start putting these options. C is row major ordering. I think there's a few different ordering options. G is the grid size. You're actually going to give it the size of the grids. And then NX, NY, NZ is how you want to place it on the node. So X times Y times Z is the number of MPI processes. NX times NY times NZ are the number of processes on a node. If you're doing 1 rank per core and J1, that's 16, right? NX times NY times NZ would be 16 on Daint. But you can mix this with OpenMP. You can do a lot of different things, so it's not just 16. So this is complicated enough. I'm not going to go through exactly how to use it, but I hope the man page will get you going. And the next slide will help you understand what we mean. So here's for 256 grids, we want a 16 by 2 by 8 processor grid. And they ran these test cases, and then they did, they always did 2 on a node, yeah, or 32 on a node. In this example for Interlagos, 32 cores. So this one he did 16 by 2 and 2 by 2 by 8 and 4 by 2 by 4. And by changing that block, I think it's relatively, you can see you're changing the surface to volume ratio of the block. And even as you change the block, you're also going to be changing the distance that the messages travel across the network. And next slide says, the end result is that what they found was a 2x2x8 block was the fastest, and it was 12% faster than the default. So they had to add this to the batch script. In the batch script, they loaded the perf tools. They did the grid order and piped it into a file, MPICH rank order, and then with this environment variable set, the MPI at startup is going to read that file. Again, I didn't go into details exactly how to do it or how you would minimize communication. Obviously, there was a little trial and error. Even in this case study, he tried at least 3 examples. My guess is that he told us he tried 3 examples, and he might have tried 5 or 6. So there can be different things to apply. But if you really find yourself in a 2D decomposition, a 3D decomposition, if your messages are larger and taking up bandwidth, one thing to try is to repack them to minimize the amount of communication that goes off node. It's not a slam dunk, and we're still learning on Cascade exactly how big of a score this is even, but it's certainly something to think about. Okay? So that was mostly my MPI talk. I'm actually ahead of schedule a little bit. Like I said, I didn't go into depth on do an iSend or iReceive. I think iSends and iReceives are better than blocking most of the time. So we'll leave that as Alfio said. There's tutorials out there about MPI, iSend, and iReceive. I wanted to kind of give you that lower level what's actually happening and why with my particular message size would I be taking advantage of asynchronous or not taking advantage of asynchronous. Any questions? Yes? Yeah? So far in our experience, I haven't been told, oh yes, this is a great thing on Cascade. But you also have to remember, so far in our experience, nearest neighbor communication in particular, most communication is taking a much smaller percentage of the time than it was on Gemini. So it might be that, oh, well, communication is going faster, I'm worrying about it less, I'm worrying about other things more, and we haven't gotten to that point yet. That's why I'm far from drawing a conclusion. If I ask myself, in theory, is this a good idea? I think in theory, sorry, didn't mean to be that adamant about it. In theory, this is a good idea. But even as benchmarkers, I'm not quite yet aware of benchmarkers on Cascade, saying, oh, I got a 12% improvement. You would think that, but it's not topology dependent. You would think that because C* and Gemini have this 3D torus, and you would think this has something to do with that 3D torus, but the two are different. And one thing was also, again, Milk, quantum chromodynamics, and a 4D decomposition. You would think with 4D decomposition and heavy communication, this would have been a good idea on Gemini, and it was a bad idea on Gemini. And as near as we could tell, it saved the amount of data going off node, yes, but it changed the paths through the 3D torus in a negative way and caused more congestion in the network and slowed things down. So in theory, it's, you would say, well, this is something I would definitely want to revisit on Aries because, with the adaptive routing and everything, we don't have those hotspot concerns in the network nearly as much. Injection bandwidth has improved, but not as much as the rest of the network. Maybe this is more important, but we haven't gotten there yet. It might be machine size too, that we just haven't played around with enough processors yet to see it. And like I said, also in general, communication is taking less time. So we're currently focused on, as machines are brought up, we're currently focused on getting the processor stable. What compiler are we using? Is the OS noisy? Hint, hint, right? You guys know that one. So we might not have hit this yet, but I still think it's going to be a good idea for someone. Any? You fill up a node first, and then an Aries chip. Yep. Yeah. Yeah. Is there a way to change it? Yes. You could change which dimension you filled first or something. Yeah. I think there are ways to change it first. I will say that I think in the discussions that I've had, the ways that are able to that you are able to change it are not necessarily recommended ways. So, like, I think there's a way to say, I don't know if this is 100% true, but you can fill up a black column on every single group before you move back around. And I've run tests where I've done that manually, but I don't think that's the recommended thing to do in general. So, and you can do that if you have a dedicated machine, which I've been known to have for brief periods of time on that upstairs. We kind of did that. We tried to spread a job across and see what we see. But those are as much like low-level testing to see how the network behaves as really a recommendation for the site at this time. We have I will say, we have our eyes open on this one. And we have theories that have been around and ideas of what we should do. The hardest thing has been we either haven't had a machine large enough to see a definitive effect, or there's not a definitive effect that says that we need something different yet. But we're watching. Right. Yeah. 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 Right. Right. I will say that most machines that are going out with a quarter to a third of the pins connected, of the wires connected, and and we actually believe that that will probably suit people, most people, pretty well. Can we come up with worst case scenarios that push that to its limit or beyond its limit? Absolutely, I can do that. Will those worst case scenarios be seen in production? I'm not so sure. You know, it might be that it evens out, and you can always upgrade the network too. So that's a possibility. A minority of people are getting the full up, and what the full up is basically going to allow you to do is forget about the optical network. So it'll be almost impossible to push it at its maximum. Yeah. You're correct. I mean, it gets as really the primary effect. It looks like at least the primary effect, if you've got a quarter of the optical, is is it in your group or not? And if you naturally fill it, I'm writing a paper that says, well, if you naturally fill it, nearest neighbor communication, the vast majority of communication stays on your group. So that seems to naturally be a good idea. And then there's some secondary effects, but we haven't been able to prove that those secondary effects are meaningful yet. I mean, way back when, if you really look at it, the black is more powerful than the green. If you really get down into the numbers, the black is more powerful than the green, and you should say, oh, you should fill a black before you fill a green. I've done those tests. I can't see a difference. Maybe someone someday will, but I can't see a difference to any placement ordering inside of a group, really. Yeah. The well, the interesting thing about this one is this one is good if you think your injection bandwidth limited, right? And it doesn't have to do with the network. And what we found on Gemini is that compared to C-Star, you were almost always injection bandwidth limited. So it was a really good idea on C-Star. With Gemini, they improved the injection bandwidth, but they didn't improve the network. And so it became less clear. For some things, yes, you improved the injection, you injected less data into the network, but you tickled the network worse, and it went slower. In theory, Aries improved the network more than it improves the injection bandwidth. So in theory, you would think this would become more important, but also in theory, you improved all of it. So it's not exactly, maybe we have to get to that point yet before we see it. We have to crank up the problem size or something, We'll see how soon we hit it. I believe it's going to help. I believe it. I have to, right? I'm a benchmarker. I got to believe that. Someday I'll use it. So I'm going to a word about huge pages and then some PGAS terminology. So you have this idea of huge pages, and most people don't think about this until they even said they were talking only about 4K pages. This is the virtual pages to physical page mapping. Well, you know, it is, in retrospect, it's remarkable that we have the same page size that we had in the early 90s. You know, literally like for 25 years, we've had the same page size. And if you look at the memory size and how much it's grown in that amount of time, with 64 gigabyte nodes and 4K pages, that's a lot of pages. And that's actually a problem if you're building some hardware resources where the number of pages matter. And it turns out that we build hardware where the number of pages matter. And so the default, which is the default? Is it site-specific what the default is? It's 4 here. So it'll run with 4K pages. I know that, but you can also try different page sizes. Seriously, it's 4K here? Boy, that's interesting. I don't know. I know it's set to like 16 in my CSHRC file. So, boy, I wonder. Okay. Nonetheless, okay, the point is that there are different modules available to switch the page size. We have 128 and 512K, but really the first one that's important to know about is the 2 meg page size. That actually fits kind of naturally in with some of the processor features as well. And I would have thought that that was the default, honestly. So you can try your page, different page sizes. I think people have tried varying amounts. Bigger is not always better and may, you know, in some cases slow down things. But I also thought, like with 4K pages, you can run out of some resources too. So I think this is something where we're really going to have to get more users on the system than the number of benchmarkers we have in-house and see where we land. But at least you know that you can load these. And okay, what good does it do to load these? If you load them and you compile and run, if you compile with it loaded and if you run with it loaded, then it will set the proper environment variables and link line things so that you will use huge pages. Your executable will use huge pages. It's relatively tricky to do it manually, which is why we do it via the module. I'm not even going to go into it because I'd screw it up myself on how to set the link line and all the different settings. So this would be kind of something to try. Heck, try CP2K with this. You know, who knows? CP2K uses large. Yeah, but you have to have it loaded when you run it too. So be watchful of this a little. So I'm less sure about the impact of MPI. I know there are resources in MPI and that there are various resources that you run out if you have 4K pages. I'm less sure exactly about when you run out of that, and I'm also less sure about if you keep on increasing the page size, if that's always a good thing. I think there's for some reason a sweet spot in the 2 to 8 range. That's what I thought for MPI. For PGAS, but I think there are some cases where it crashes. Yes. Do you remember where that limit was? Was it like 256? because I think that there's like no one goes above 256. Yeah. Just push it until the machine croaks. And actually, one can also see that the larger the page size, there's a higher probability of running into memory fragmentation issues. So that's, if you really are trying to try large page sizes, there's a chance that you'll run into that, and it'll stop. Your job will stop running. So it's not that I'm recommending immediately try 64 meg pages, but you know, I would probably recommend trying 2 and 8, for example. And I know PGAS, there's some other all-to-all patterns that benefit from larger pages. 2, I mean 4K, it's just like sucks, and 2 is better, 8 is better, 16 is better, depending on exactly what's going on. So. So yeah, there is let me get this right. Gemini, the internals of Gemini, when you really get down into the internals of Gemini versus Aries, there was literally a fixed limit of the number of pages that Gemini could manage or know about. And I mean, that fixed limit, I think, was in the thousands, but it wasn't in the hundreds of thousands. And if the memory size got big enough and there was yada, 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 you would need more pages than what was in Gemini. And so you would start to error out these things. In Aries, they actually implemented something more similar to a TLB cache in Aries. Okay, so it no longer is a functional issue if you have more pages than you have entries in this TLB cache. It no longer crashes. It's just a performance issue because you can actually start to thrash that cache. And that's why the PGAS is the one that's more likely to hit it than MPI. If you do larger messages, and I'm not saying megabytes even, but if you're doing messages of kilobytes and stuff like that, it becomes much less of an issue in general. And that's generally speaking how MPI is written, right? MPI is written to, like you just said, your question before, most people buffer up and don't send just a couple words. They send hundreds or thousands of words. And so that performance implication is greatly reduced, and this page TLB implemented in Aries works pretty well. But yeah, some people don't think about it, but there are resource limits in Aries, in Gemini. So okay, as long as we have time, and I think we do have time, 15 minutes or so, I'm going to talk about PGAS terminology and internals a little bit. I'm not going to give you a course in PGAS. I'm going to have like 2 slides that show even how to do a PGAS transfer in CoreArray Fortran. But I at least want to, whet your appetite. If you think this sounds interesting, then you can research more or contact us for more information. What do I mean by PGAS? I actually lumped 3 things all together. It refers to partitioned global address space, and that basically means I can calculate the address of a partitioned space. It's not just that I can calculate the address of my shared local memory. I can do it across the machine. The languages that do it are UPC, which is a specification, which is an extension to the C language. CoreArray Fortran, which has actually been adopted in the Fortran 2008 standard and implemented. And this was pretty easy for Cray to to implement. We had an early version. They decided to change the spelling on a few things, and we changed the spelling on a few things. And then SHMEM, which is a library-based thing. I count it as PGAS because its behavior is so similar. Technically, it's a library. It's not a language. You can use it in Fortran. You can use it in C. But I just lump it in. So SHMEM is a library-based. It's not the part of any language. That has the advantage of its compiler independent. If you are compiling with GNU or Intel, it doesn't matter. You can use SHMEM. Our SHMEM will work with those compilers. The compiler has no knowledge that you're compiling a PGAS code. It just knows it's a library call. The basic rules of library calls apply, but it's not going to do any data flow analysis or typing or any kind of transformations or optimizations associated with that. This one's slightly out of order, actually. I'm going to go here and then go back. So the PGAS terminology continued. UPC is a specification. It is not a standard. Basically, some people wrote a paper, and every year they have a conference and argue about what they think should be in the standard, or what should be in the specification, but it's not in a standard. But it is integrated into a language. There's enough there that we are able to implement it, and there are some customers that really like it to use it in production, and some customers that like to play with it, so we have it. It is heavily compiler dependent, okay? And by heavily compiler dependent, I mean you must compile with the Cray compiler, basically, to do this. Certainly on our Cray machines. Other people are dabbling with it. There's a UPC Berkeley compiler out there. If you do UPC Berkeley on Google, I think you'll be taken to a web page where you can actually write a UPC code, paste it into their web page, hit compile, and it'll do something. It'll return something to you, whether or not it was able to compile. The point is, it's heavily compiler dependent. It is very flexible, but I would say it's filled with challenges like pointers and the lack of true multidimensional arrays, and the number of options for distributing data. Well, that's pretty much true for C and C++ in general, one could argue. I mean, pointers, it's great for playing lots of tricks, and if you're really good at it, you can say, oh, I do this and this. But I mean, really, when you get down to performance and understanding and debugging, there's as many challenges as that. And in particular with multidimensional arrays, some things become less than natural. Now, Fortran 2008 incorporates coarrays. Again, very compiler dependent. Basically, you use the Cray compiler on the Cray hardware. Intel has started to dabble in this so that you can play with it on a couple of other Intel platforms. But this is what's available you use the Cray compiler on Cray hardware. In a way, it's philosophically different than UPC. UPC takes the idea that I want to put some keywords on some variables, and now those variables are accessible by anyone in the job. CoArray Fortran says, I'm going to fundamentally make it obvious when you do a remote communication. So I change how a variable is declared. That makes the variable, replicates it across every single image they use is their terminology. Replicated across everyone, and then if you use brackets, that means you're communicating with something remote. If you don't use brackets, it means you're communicating with something local. So all of your code that just wants to compute on local stuff and doesn't know anything about brackets, it continues to work. When you add brackets, that's obvious. I'm causing a remote communication to happen. So going back to this slide, and now slide 38, PGAS, partition global address space. It is a single program, multiple data. So this is not like multiple binary launch. You can't do multiple programs and still get them communicating through MPI. That's possible in MPI. It's not really possible with these languages. Single-sided communication as opposed to two-sided communication in MPI. Yes, there is one-sided MPI communication, but that is honestly rarely used. I would even say PGAS is more common than single-sided MPI. Explicit synchronization is required. So there is, when you do a put in any of these languages, it just happens. It doesn't say anything about where the sender or where the receiver is if you're doing a put. When you do a get, it doesn't say anything about what the PE that you're getting from, where it is. It doesn't have to know anything. MPI is mostly implicit, like we just had with that rendezvous thing. You know, the synchronization happens between I'm going to issue and send, you're going to issue a receive, and there's going to be a bunch of handshaking that goes on underneath to make sure we're talking to each other and passing the right messages. These languages tend to give compilers a lot of freedom. You can put them in the middle of a loop, but I would say it might not be the best idea to put them in the middle of a loop. But you can put them in the middle of the loop. And you can, you don't have to worry about typing. You can actually transfer a single to a double across the Cray Fortran, and the compiler says, oh, I know what you're doing, I'm going to do it for you, sort of thing. And then it turns out that many algorithms are very naturally expressed using one-sided communication. Halo exchanges, yes. Nearest neighbor, yes. But I am finding that you know, if you just take something that was easy to write in MPI, like a nearest neighbor communication, and you replace it with PGAS, you might go as fast, you might not go as fast. You might go a little bit faster if you play around with it some. Where someone is calling me from the United States. Okay, I'll just ignore that one though. I'm not going to pay the $2 a minute or whatever. Where was I? When PGAS really has an advantage is when you're finding it's difficult to program something in MPI, or you're issuing lots of MPI messages or small messages, or maybe just the two-sided thing, it's difficult to build an algorithm with a two-sided thing. You're having to jump through a lot of hoops. One-sided sometimes can just completely blow the doors off this algorithm, and you get a major speed up in that section. So I think these PGAS and MPI are going to continue to coexist for quite a while, basically because we're not getting rid of MPI, and we're going to find places where PGAS as a section of the code can win, and those will be inserted into sections of the code. But perhaps, you know, most of the code is written in MPI, if you know what I mean by that. So a couple of other terminology things. Under this, there is actually two other things. Live PGAS, that's a relatively thin library that the compiler translates the UPC and Cray Fortran language into PGAS, or into the live PGAS, and then it's those calls that turn around and go even to the next lower level thing called DMAP. DMAP is the low-level communications library that implements off-node communication functions. DMAP doesn't know anything about on-node transfers. It knows about off-node transfers. We've said DMAP, the term DMAP a few times. DMAP collectives, we said. We hinted that DMAP all-to-all is coming in MPI. All of these things, SHMEM, UPC, and Cray Fortran, all translate down to DMAP. And that's one of the reasons why I lump them all together, because if it's performance-wise, really you can get the same performance out of all three if you're careful. You might have preferences as to which one you use, but they're really, all three are similar if you put a little time into it. So a couple of Fortran examples, not that I'm trying to influence you on which way to go, but here's just an example of, so we have this allocatable array, array A and C. We're going to allocate it, and when we declare it, we have these brackets with a colon. When we allocate it, we have brackets with a star. Brackets with a star just means, that's the convention to say use the same number as you have the number of PEs in the job. So whatever is on the -n, small n of your app run line. And of course, since this is Fortran, it starts at 1 and goes up to the number of PEs. Then later on in my job, this is what we would call a put, right? I have ABUF, which presumably is some kind of local buffer. I'm using array syntax that says copy the number of I-size elements out of ABUF and put them into C, where the remote image number is RB. The brackets say I'm doing a put, well, the brackets say I'm doing a remote reference. The fact that they're on the left-hand side means I'm putting the data. I'm sending my data to you, putting it into your memory space. The array syntax says I'm going to do a number of them, and the big A out front, if you remember from our listing file, says this was pattern matched. And it turns out that's relatively important to performance, because you don't want to do these single word at a time. You want to do this as a block transfer, and the pattern matching is how you do it as a block transfer. This number is for Gemini, so a large contiguous puts can get 3 to 6 gigabytes a second. It's really easy to get pretty high performance on this stuff as long as it's pattern match, and that's why I say look for the A in the .lst file. On the other hand, it's also possible to write things that are less than well performing. In this case, X is a two-dimensional array locally. I still have this bracket star for the remote image numbers, and I wrote array syntax again, but my array syntax is over the second dimension. And since it's over a second dimension, it's transferring one word out of every single column, and there's a stride between words. And I have a longer presentation that basically says, that is very inefficient. It's the natural thing, and Intel said it, the smallest unit that is transferred around a processor is, or a local node, is a cache line. So if you're doing a single word transfer, the cache line is 8 words, you're already throwing away 7/8 of your bandwidth. And that's sort of just the beginning. If there's actually more things that are preventing use. It's a very rapid ramp. So you can get a max bandwidth, if you're careful, you can get max bandwidth with 16 contiguous words. You don't need 1K or 2K. You can get it with a very small, but single word is not too good. And in fact, single word puts is, in this case, getting 0.1 gigabytes a second. That should have gone up. That might be up to a half a gigabyte on Aries. I'm not too sure. Nonetheless, it's not as good as contiguous transfer. So if you're ever programming in PGAS, it's worthwhile to buffer up at least a little to get at least a small number of contiguous words, at least in the teens or maybe in the hundreds. But you don't need to buffer up to thousands. You can fire off hundreds all day long, pretty much. And that's all I have on PGAS. It's just a little bit to whet your appetite if you're interested. But I'm basically at my hour-and-a-half limit and voice limit. So are there any other questions? This is my last talk. I will be around this afternoon, but is there any other questions that someone wants to ask me about off-node communication or the Aries in general? Yeah.
So I guess we're one of the places which plays around with PGAS, and we had a lot of difficulty finding any cases where PGAS could perform better than the MPICH side. And only very special circumstances where you use
we do have cases, and I'm not surprised that you say that. I don't know exactly what your transfer pattern was. For quite a while, if you're writing an all-to-all, the fastest way to write it was in PGAS, for example. We also have integer sorts that do PGAS, and that was that's better than MPI two-sided sort of things. I think I said this before, if you're talking about a nearest neighbor communication, it can actually be pretty difficult to even match MPI. MPI, I think it turns out that for the simple nearest neighbor type of thing, MPI is just about, you know, I won't say exactly what you need because I just can't bring myself to say it, but it is what you need, right? It's that point-to-point communication and handshaking that is good for the nearest neighbor type of thing. I'm sending to you, and you're the only one that needs to know that I'm sending to you. In the PGAS languages, they were built up to where they revolved around global barriers, right? I mean, that was the main way of doing things is everyone communicates and does a global barrier. Or maybe you even have to do a global barrier to make sure everyone is ready to communicate, and you do a global barrier. And that's actually a pretty bad idea relative to MPI because that guarantees that everyone is communicating at exactly the same time. MPI actually has quite a bit of flexibility so that different people can get to an I send or I receive before other people. And that spreads out the communication just enough that that's a good thing. So I'm not surprised, especially if you're taking an MPI program and converting it to PGAS. It's not obvious always how to do it. You have to do some more things like pipelining, you know, some of the communication or something like that, or be careful how you do I think they're. Oh, I hope I'm not letting something out of the bag, but Berkeley did a paper with UPC, and they basically said if you just put it in there, you know, if you just put UPC in there as block transfers, it didn't do, and these global barriers, it went noticeably slower. If they rolled their own synchronization, kind of with flags handing it back and forth, almost like you might imagine is implemented in a MPI, only much lower level, they were able to get quite a bit better performance. But you know, that was with some work. So you kind of, with PGAS, you know, I think PGAS will evolve to the point where they will be able to match MPI even on these nearest neighbor things if they get some more synchronization semantics. Right now, PGAS is best if you like, okay, I need to do something that is either hard to do in MPI or I can't do an MPI, or this expands the capabilities. Another case that I'm aware of where PGAS was better was in some climate code, and they were doing a transpose, I think. And they were computing, creating the data, and once the data is created, they could issue a send immediately, and then they could go on to the next outer iteration and create more data. And the natural way to program that was do all the computations followed by an MPI all-to-all. In PGAS, they put the communication, the put, right in the middle of this outer loop, and overlapped better than they would have otherwise. And so that was another example. But again, it's not. Even there is, it's not that they just replaced the communication with PGAS. It was, they did something more. Yeah.
And the other one is essentially also a nearest neighbor code, but with an unstructured, rather unstructured communication pattern.
Okay.
Both sort of fit into that MPI.
Yeah, and the unstructured was there still a relatively limited number of neighbors, well well-bounded, maybe less 10 or something like that. Yeah, and I'm guessing if you did PGAS, you had to use a barrier. If you did SHMEM, about the only way to do it was a barrier. Yep. Yeah, and you know, I say this about every 6 months. If I ever write a book about supercomputing, you know, I'm going to title it The Heisenberg Uncertainty Principle of Supercomputing. Because really, if you're talking about performance, the less you know about where your code is at, the faster it will go, if you think about it. The more out of order, this is true at the processor level, the more out of order the processor, the faster it goes. The more uncertain you are about where the data is, what level of cache or even in memory, the faster it goes. The more processors you have, hopefully the faster it goes, and the fewer barriers and synchronization that you have, the faster you go. So anything that probes the system and says, I know where you're at this moment, it probably means it had to slow down to tell you, you know. So, and so that's exactly what I am personally finding with those communications. Those barriers are killers, and you need to do something else.